Welcome everybody to Probability and Analysis webinar. Today we have Brad Wick from the University of Washington in St. Louis, who is going to talk about singular integrals on the Fock space. Please, Brad, feel free to start whenever you're ready.
Okay, thank you for that introduction, Pata. Let me thank the organizers of Probability and Analysis webinar. So Polona, Irina, Pata, Tomasz, and Beatrice Helen for the opportunity to speak. I'm going to try to set a low bar at the beginning. That way, in case I make mistakes, you'll all be forgiving. I'm a little under the weather, and so I apologize if things aren't completely clear, but I'll try to do my best. So I want to talk about a somewhat recent project. We can call it a Corona theorem in the sense that it was proved during the time of Corona about singular integrals on the Fock space. And I'll tell you what I mean by this and tell you the question that was raised in operator theory by Zhu. And it's based on some joint work with these mathematicians here, Guangfu, Jili, Minxing Shen, and Mixin Yan. 3 of these were at Macquarie University when I visited, and that's when this project came about. So let me try to tell you the story and set the background, and we'll go from there. So we're going to talk about the Fock space on Cn. And so this is going to be the collections of functions which are holomorphic on all of Cn, such that if you integrate over Cn, against a certain measure, it'll be finite. And we will just take a square root to turn this into a norm. And now this d lambda of n is, d lambda of z is the probability measure on the space, so the Gaussian measure. I guess since this is connected to probability, everyone in the audience probably knows this, but for those who've never seen the Fock space before, maybe we just go this way. So it turns out that this space here, F2 of Cn, is something called a reproducing kernel Hilbert space. And so this means that point evaluation is given by inner product against a special function where, and I didn't say it, but if I've given you the norm, of course, you can dualize this to get the corresponding inner product. And this function kz of w is e to the w dot z bar. Just so we have it going forward, let me just remind you of the norm or the inner product. Okay. And notation that we'll use at various times as well is going to be kind of an abusive notation, but it's reasonable. If I write z times z, this will mean the inner product of, let me write it differently, z times an x, this will be zj times xj. And so if I write something like z squared, this will be z dot z, where it's an inner product, okay? So this is the space of functions we're going to be worried about. And now we're going to talk about this other space of functions, or this harmonic analysis connections. So we'll introduce something called the Bargmann transform, which is this integration operator. And so it takes in a function in L2 living on Rn, and it defines a function which lives on Cn because it becomes holomorphic because this exponential will live up there. These other things are just defined so you have normalization. But the idea is it takes in an L2 function and it returns a Fock space function. And that's the content of this lemma that says the Bargman transform is some unitary operator between L2 on Rn and the Fock space on Cn. And it's a one-to-one onto an isometric. So it tells you that the L2 norm of the function can be understood in terms of the L2 norm of the Bargman transform. So this will be a translation between Fock space functions and L2 functions, as the story unfolds. So this was the theorem or the question, but this is the question that was raised by Kei Zhu, who's an operator theory person at SUNY Albany. And he wanted a characterization of the functions which belong to the Fock space so that the following integral operator is bounded. So you're going to integrate against a kernel that looks like this. So you have this kind of exponential piece, which is coming about from the reproducing kernel. And then you have this extra piece here that is somehow should be thought of as like its action on the imaginary axis. If Z and W agree, that's really what it is. It's the action on the imaginary axis. So you're somehow measuring in that language. So let me motivate this question a little bit with some examples. And then I'll tell you what the theorem would be. So this was the problem that Zhu posed in a 2015 integral equations and operator theory paper. We want to describe these functions phi. Okay, so the first example, let's take the obvious thing. Let's take phi of z to be the function which is constantly 1. So I would substitute 1 in here, and that term would then just go away. And then I would have f times this function. But that is the same as the inner product of f against this kernel in the appropriate space. And so you can then compute that s phi f of z becomes integral over Cn of f of w e to the z w bar d lambda, which becomes the inner product of f against kz, which just becomes f of z. Okay, so that's the trivial example. S sub 1 is the identity operator on the Fock space. Okay, let's go to the next one. Example 2. We're going to take phi of z to be e to the z a bar. And so then you can compute s phi of z. And so you write out what it is. It's integral over Cn, f of w e to the z w bar, e to the z minus w bar, a bar, d lambda of w. And you make obvious changes of variables. And you can write this as e to the z a bar integral over Cn, f of w, e to the w bar z minus a d lambda. And this last integral you can compute as e to the a minus a bar times z plus mod a squared over 2 times w a bar of f at z. And this function wa is the so-called Weil operator. So if we were on Euclidean L2, you have an obvious translation, and Lebesgue measure is translation invariant. However, the Gaussian measure doesn't respect that as well, and so you have to build a factor into the translation operators that somehow works well with the change of variables. And so this becomes e to the z a bar minus mod a squared over 2 f of z minus a. And so if I did the computations right, this thing will be bounded on f2 if and only if so the whole point was this was s phi when it's all said and done. So the translation operator, the while operator, is bounded on the Fock space. But this factor of a could hurt us. And so in fact, I need a to be a real number. And this is because pointwise multipliers on the Fock space are just constants. That's the content of this. Okay, so the next example is the one where I think Zhu came up with the conjecture. So let me define a function here, a of z to be the integral from 0 to z, think of it as the antiderivative if you want, of the Gaussian. And we'll see a theorem that will help us figure this out, and we'll define phi of z to be minus 2 over square root of pi, a of z over root 2. Now, here, I want to say what this h is. So remember, we have this intermediary, the Bargman transform, that moves between L2 and the Fock space. And so B inverse will move the Fock space to L2. I'll have an operator H, which will act on L2, and then I'll have an operator that will map from L2 to the Fock space. So this operator T will act on the Fock space and produce Fock space functions. And here, H is a beloved operator in harmonic analysis. It's the Hilbert transform. And so, again, this is probably well known to everyone in the audience, but again, up to constants, it looks like this function here. And you can then compute using the Fourier transform that this becomes this quantity here. And so this function, this operator T, becomes S sub A of F in the language of that problem from Zhu, or S sub phi, sorry, where phi is defined this way. That's this piece here, this piece here. And so this operator is bounded on the Fock space because the Hilbert transform is bounded on L2. That's the crux of the story. The way Zhu found the function A is he proved that this function phi satisfies this differential equation. Which is where this antiderivative comes in, right? If I undo this quantity here. Okay, so those are all the examples to keep in mind. There's like the trivial example. There's the example of translation on L2 that gets pushed over to the appropriate translation on the Fock space. And then there's the example of the Hilbert transform. So those are the motivating examples that Zhu had when he came up with this conjecture. So now let me tell you the story. So the main result, and then we'll kind of give you some of the ideas that go into this proof. So we're going to have this operator, S sub phi, acting on a function f, and you're going to integrate the function f against this kernel coming from the reproducing kernel and the action of the function phi. And Zhu wants a characterization of the functions phi. And so the way you characterize those functions phi, it turns out that this operator S sub phi will be bounded on the Fock space if and only if I can find a function m, which belongs to L infinity, so that my function phi has this representation in terms of the function m. So you should think of this as some sort of like holomorphic extension of the function m from Rn.
Brett, what is there, x minus 1/2 z or I over z?
That's I over, I can make that a little bigger.
I over 2, okay.
I over 2, yeah.
Okay.
Yeah. From our perspective, it's nice that we can actually completely determine the norm in terms of the symbol m. So the norm of this operator S phi will be exactly the norm of the L infinity symbol. Now, for those who are familiar with harmonic analysis ideas and the fact that I told you the story is connected to the Hilbert transform, you might then conjecture a way to prove said theorem. So let's continue with the story. So I'm just going to give you some theorems and facts, and then we'll prove them towards the end. That way the story is all contained, and then I can make the, if I don't have time at the end, I can just say, well, I'll point you to the paper. So one of our tools is going to be the Fourier transform. And so this will be denoted a couple different ways. It might be denoted with the calligraphic F, it could be denoted with the hat, but again, it's just integration against this complex exponential. And that shouldn't be so hard to believe that this is going to play a role because of this function here and this quantity here. Okay, so one of the main ingredients in the proof is the following proposition, which you can find, for example, in Grafakos's classical harmonic analysis. And it says, suppose you have a bounded linear operator that maps L2 into itself. Then a necessary and sufficient condition that T commute with translation. So on L2, I have obvious translation, just translation in the variable. So I want T to commute with translation is that there exists a bounded measurable function M, the multiplier, so that the Fourier transform of T applied to F is multiplication on the Fourier transform side of the Fourier transform of F. So again, maybe in shorthand, we would write it as this: TF hat is MF hat. And the norm of T on L2 is the norm of this multiplier. That's the harmonic analysis fact that we're going to explore. Okay, so lemma 2.3, I would like to understand this Fourier transform function acts on L2 functions. I would like to understand what that becomes on the Fock space side. And again, we have the Bargmann transform that moves things around. So if I pre and post compose the Bargmann transform with the Fourier transform and act on a function, I should see what happens. Well, it turns out it's just multiplication by I or minus I in the appropriate context. Okay, so this computation, this lemma is just kind of definition pushing. You move things around in exchange and everything's totally fine. Okay. The next lemma we will maybe come to a proof of, but I just want to give it to you as a fact for us. It says that if I take an L infinity function, and if I do the things that appear in this theorem up here, that function belongs to the Fock space. And that was one of the things that we needed to have this function, this operator somehow make sense. So it says that if you take an L infinity function, then this function phi lives in the Fock space. The proof of this lemma is going to be more or less straightforward computations with Plancherel and Cauchy-Schwarz. That's the idea. Okay, so now I didn't define this earlier. So let's let M22 of Rn be the set of T's such that T satisfies this proposition 3.2. So this means either that T's commute with translation, or you could think of it means that T is given by multiplication on the Fourier transform side, or you could think of it as T is given by convolution on Rn. So if I kind of do this pre and post composition by the appropriate Bargmann transform applied to such a T, so remember such a T is associated to a multiplier, I can see what that multiplier does. And here you're getting kind of the function phi that is going to play a role for us. So this is the analog of our function phi. And then lemma 3.3 is going to tell us that if I'm a bounded operator S phi, I can construct the multiplier T. That's going to be the point of this. Okay. So these are just some technical lemmas. I'll state them again as we need them, but I want to kind of give you the flavor of the stuff that goes into it. Sorry, and then one last one. It says that for t, which is given by one of, let's call it Jou's operators, the S sub phi, you can define M in an obvious way, where M is given by this double integral. So we have all the machinery we need to move back and forth between every parts of the proof. Now, before I prove the theorems and tell you about the proofs, I want to tell you what you can actually get with this, because what we have is we have this nice theorem that tells us how to determine the norm in terms of the norm of the symbol, and that lets us actually deduce a bunch of operator theory corollaries along the way. So for example, theorem 1.2, it says that if we have that S phi is bounded, then the adjoint of this operator is simply given by the same operator, but with it's a little small S phi tilde, where phi tilde is kind of built from the original thing, but with a complex conjugate in the appropriate way. So basically, if I take adjoints of S phi, I take complex conjugates of the symbol. That's the content of the theorem. And it lets you determine that the S phi is being normal. We'll talk about theorem 5.1. It says that the set of S phi's such that S phi is bounded is a commutative C star algebra. Again, this shouldn't be hard to see at this point, because we have this tool that says S phi's are basically given by convolution operators with a bounded symbol. Then L infinity has this nice commutative C star algebra property. So the S phi should have it through some appropriate language. And you can deduce compactness. So S phi is compact if and only if the symbol is 0. That's the point. So these are the operator theories, corollaries you can deduce. We won't prove all of them, but I'll give you a flavor of them as time goes on. I want to go back and forth and kind of tell you how I told you what the phi should be in those early examples, and I want to tell you what the corresponding function M should be to show that it really does work out the way it's supposed to. So you can just check that if phi was 1, we saw in that case that S phi became the identity operator, and then the M has to be 1 to make this all work. This example, so 31 is this paper by Jou where the story comes from. He considers these kind of, let's call them quadratic Gaussians. And he then computes that this is bounded on S phi, or this S phi is bounded on the Fock space. And he then can, so by the theorem I told you, you want to know what the M should be. And so then you need to compute this kind of equality. This left-hand side is what phi should be. The right-hand side is kind of changes of variables and completing stuff. This whole expression needs to be a constant if it's going to work. And so that lets you say that M of X has to be kind of canceling this factor here. Okay. If you consider the reproducing kernel, then you can go through and check that the function has to be given by this sort of expression here. And in fact, S phi will be bounded if and only if A is a real number. And we saw before when I took this reproducing kernel that the S phi became this while translation, the while operator. Okay, let me give you another example that's in the language of harmonic analysis, because I know there are people that I saw in the audience who would be very interested or care about this connection. So if we take the Rees transforms on Rn, so I write it this way, and you can of course write this in convolution language by making the appropriate change of variables. So this becomes some kj of x minus y, f of y, dy. And then, as is probably well known to everyone in the audience, the Fourier transform of the Rees operators just become multiplication by something. And this is the symbol of that Calderon-Zeeman operator. And so you can then kind of see this as, in this language, it's Fourier, inverse Fourier transform, multiplication operator Fourier transform. And so if you apply that main result, you can deduce that the phi j's have to have this this particular structure. And then I guess we also know that if I sum the Rees transforms, squared and take their Fourier transform, well, this becomes sum I squared Cj squared divided by mod C squared. And so this becomes -1 in the end. And so the sum of the Rees transforms is minus the identity. And this in particular implies that the sum of the S phi j squareds behaves like minus the identity. So you have an operator identity that exists for this collection of operators S sub phi. Let me also say I won't give them more examples. We have things for Berling operators. Again, because it's a Fourier multiplier. You can write down, you can figure out what the symbol m and phi have to be for this all to work. Okay. Let me go through and talk about, we'll go back and talk about some of these proofs again, and I'll try to give a proof of the main theorem. So for the time being, let me skip Lemma 3.1 because it's just a technical computation. I won't go through that. Let's talk about this lemma here again. So remember that T's in M2 mean that M22 mean that their Fourier transform satisfy this identity. So we have the property that T F hat is M F hat. Excuse me. And this is asking us to compute the Berling transform of T composed with the Bargman transform of T composed with the inverse Bargman transform. And so the proof of this is just direct computation. So we won't say more on this one. But we'll need it at some point for the story. Same with this one here. This is just how the Bargman and the Fourier transform interact. And again, this is just direct computations with moving integrals around. Okay, so let's go through this proof of lemma 2.3. So this one is, sorry, lemma 3.3. This one's saying that we know our S phi operator is bounded, and I want to show that there exists this function, or this operator T that maps L2 to L2, and I want to show that T commutes with translation. So let me set up what we would have to have work for this all to make sense. So let's set T to be B inverse S phi B. Okay, so B was Bargman. And this maps L2 to Fock. And B inverse maps Fock to L2. And so if I have set this up right, this is now a map from L2 to L2, because the Bargman will take an L2 function, produce a Fock space function, S phi acts on the Fock space and goes back into the Fock space, and then B inverse goes from Fock to L2. And then, so we know that T is bounded on L2. Excuse me. This is since B is an isometry, and since S phi is bounded on Fock space. So we need to show the following. I need to show that translation by A acting on T is the same as T composed with translation by A. And here, translation by A acting on a function at X is the obvious translation on the L2 side. So if I show T commutes with translation, then by that harmonic analysis fact, that would say T f hat is the same as M f hat, with M as an L infinity. So what you do is you compute what the translation becomes under the action of the Bargmann transform. So this is a computation, again, just using changes of variables, and this becomes this while operator. And so what we will compute is we'll compute translation by A acting on T. And so this will become translation by A, B inverse S phi B, which we will write as B inverse B, translation by A, B inverse S phi B. And this term here became this while transform. And so you get this quantity here. Okay, so some of this is just simple operator theory, some of it's a computation. You would then also compute, run a little out of space, let's see if we can get it here. You would also compute translation by A with T. And I want to know that those two things are, so the question is, are these two things equal? And you compute doing the same computations. And you get that this becomes B inverse S phi WA B. And so then you're left with the question of, is it true that WA S phi is the same as S phi WA? And it turns out that you can check that by hand because the operator is somehow convolution type, and so the translation will work well. Okay. All right, so let's me now try to give you a sketch of the proof of the main theorem. So again, this will only be a sketch. All right, so what we do is we're going to use lemmas 3.3 and 3.4 to get some function which belongs to L infinity such that S phi of F is the same as the following. Okay. So I know I said this before. I said that kind of this change of variables argument gives you a candidate for what this thing should be. So what we'll do is you'll set phi 0 of z to be kind of the function that exists there. We'll call this star for a moment. Integral over Rn and x e to the minus 2 x minus I over 2 z squared dx. And then you need to make a claim that phi 0 of z is the same as your given function phi of z. And that would prove the theorem, provided you were able to demonstrate that. This equation star, so remember S phi f of z was the integral over, again, a constant I probably have lost, but it's okay for the moment, e to the z w bar, and then it was phi of z minus w bar d lambda of w. And so equation star implies that for any f in L2, not L2, I'm sorry, for any f in the Fock space, you get that 0 is equal to the integral over Cn, f of w, phi of minus w bar minus phi 0 of minus w bar d lambda of w. And at this point, you should kind of think, well, I'm testing over all possible functions. I get that the difference of two functions is orthogonal to all possible functions. The only way that can happen is if those two functions are the same. And so there's some duality and a little more kind of identity principles for complex functions. But the idea then becomes that this says that phi of z has to be phi 0 of z. So you should think of this as some sort of duality argument. Okay, so that's a rough sketch of the proof. You use these lemmas, these kind of simple lemmas, to say that something has to be given by this L infinity function, and then you equate things and show that really it is the right thing. Let me go back to the lemma theorem 5.1 to connect you to some operator theory. So this one says something is a C-star algebra, and so let me give you a proof here. I want to connect the idea to L infinity. So again, L infinity is a C-star algebra. That's the obvious thing. So you have phi j, and you should think of it as kind of the operator with T mj, and you should think of multiplication by m, which is just acting on f, to be m times f. And so I want to somehow understand the composition of two of these things and show that it becomes some new function to live back in the space that would get me back into this commutative algebra property. Okay, so what you're going to do is you're going to compute S phi 1, S phi 2, acting on f, and you're going to then just see what this becomes. So let's see if we get this right. This will be Bargman inverse Fourier transform, multiplication by M1, Fourier transform, Bargman inverse. So this is the operator S phi 1. And then you would have the same thing with the other one, Bargman F inverse multiplication by M2, F Bargman inverse. And this will be S phi 2. And I guess you can see, hopefully people can see the colors, that this one would cancel with this one would cancel with this. And so when it's all said and done, this becomes Bargman, Fock, or Fourier transform inverse. The two multiplication operators will, of course, commute, M1, M2, F inverse, and this M2. This you call M, M1, M2, which is the corresponding idea with phi. And so this becomes some operator S phi, where phi has the appropriate symbol given by things. And of course, because multiplication operators commute, then S phi 1, S phi 2 commute. And then you can check the other properties of something being a C-star algebra in similar ways. So I told you about the adjoint and what happens when you take the adjoint. It becomes an operator of the same type. It's just you take the complex conjugate of the symbol. The key point is, since you have this identity or this principle that lets you take the symbol and push it to L infinity and say the behavior of the operator is the same as the L infinity norm of the symbol, all the operator theory facts you want can kind of be ported over. Okay, so let me give one last fact for people who might know things in this area. So a question that people frequently ask is the following. Does the reproducing kernel thesis hold? Okay, so what does the reproducing kernel thesis say? So we have this function kz of w, so the reproducing kernel, and it was given by this inner product here. And we will let little k z of w be the normalized reproducing kernel. So the norm of little k z in the Fock space 2 is 1. Now, we would like to understand the action. So does action of S phi on kz determine if S phi is bounded? That's the content of the reproducing kernel thesis. So you can go through and compute very easily what this S phi will do to a reproducing kernel. So you just plug in the definitions and compute. It becomes this sort of expression here. And so then the question we're somehow trying to ask, is it the case that S phi is bounded on the Fock space? If and only if, okay, now let's see if we can't get an obvious condition here. So if I take S phi being bounded, then if I use this identity that we've just computed, and so I look at S phi k z, this would be equal to the inner product of phi of w minus z bar kz comma kz, and so this becomes phi of z minus z bar. And now we would take absolute values, and so then if S phi were bounded, then the right-hand side would have to be bounded because obvious reasons. So you hope the conjecture says that the sup over z's in Cn of phi of z minus z bar is finite. So this direction is true. The reproducing kernel thesis in this form is asking, does this question hold? Can we go the other direction? Another way to phrase this is you're trying to understand if the action of S phi on the Fock space can be determined from the action of phi just on the imaginary axis. And the answer is no. Answer. And I'll tell you roughly how the idea would go. So what you do is you let psi belong to L4 of R, but not L infinity of R. And you'll define phi of z to be the integral over r of psi of x e to the minus 2 x minus I z over 2 squared dx. Okay, so then you can show that phi belongs to F2. And you can show via Cauchy-Schwarz that phi of z minus z bar sup over z is finite. Okay, so I have a function, I have an operator s phi, I have a function which is bounded on the imaginary axis, but then you can equally show that phi of z is not equal to an integral over r of m of x e to the minus 2 x minus I over 2z squared dx for m in L infinity. And this is a slightly more involved argument, but the point is that this was another question that you raised of, well, maybe this simple test of the behavior on the reproducible kernels alone is sufficient to understand the story. But unfortunately, no, you actually have to test much more. That's the bottom line. So I think in the interest of that basically being my time and me having to go deal with teaching and other things, I will stop here in the event that there's a question or two before I have to run off.
Thank you very much, Brett. That was a great talk. Are there any questions? I have a question. You know, since you are working with a Gaussian measure, it seems reasonable to ask if you have operator bounded on Gaussian functions, e to the power negative matrix A times z comma z, where A is it's chosen such a matrix is chosen in such a way that this result is in L2. If you just check on such kind of Gaussians.
So you want me to, instead of checking on this collection of functions, check on something like e to the A z comma z?
Z comma z, yes. And matrix A's are negative semi-definite, or they are chosen in such a way that this result is always in L2.
You know, I did not
overall
check
such matrices.
Yeah, sure,
yeah,
I understand.
That's very natural thing to try, because you work with the Gaussian measure in the Fock space. Yeah.
I didn't check this, Pata. That's a fair question. So you want me to check, I don't know how to phrase it exactly, something like this. S phi of e to the A z comma z in F2, and you want this to be equivalent to the norm of S phi as a map from F2 to F2.
Yeah.
And you take the sup over all appropriate matrices.
Yes.
That's a great question. I don't know. I did not think about that.
And another quick question. I don't know, are there any LP versions of these statements, or everything is very rigid to how can you do anything in LP?
Things break for different reasons and different sides. So on the harmonic analysis side, we don't have a good description of the multipliers that are bounded on LP. So that's one part it breaks. On the other side, this Bargman transform breaks in certain ways for p bigger than 2 and in other ways for p less than 2. So it really is kind of rigid in the sense of it needs Hilbert spaces on both sides of the story to go. You could ask other questions about, instead of having this convolution type structure, phi of z minus w bar, could you have some other kernel type structure there? And then is there some sort of maybe hidden T of 1 theorem that you could exploit? But I don't have a good sense of what the right formulation of the conjecture might be in that language.
Okay, thanks, Brett. Any other questions from audience? Okay, if there are no any questions, let's thanks the speaker again.